Great, thanks for the introduction and thanks for inviting me. So, right, like Peter said, today I'll be talking about implementing the fast multipole method on a quantum computer. And this is actually ongoing work that I think has involved discussions with several different people at Quantum AI's algorithms team. But at least what I'm going to talk about today is in collaboration with Dominic Berry and Ryan Babush. Okay, so what is the fast multipole method? Well, the fast multipole method, or FMM for short, is a classical algorithm for computing the potentials due to two-body interactions between a large number of particles. In particular, it speeds up the computation from quadratic cost, as for the naive approach, to linear in the number of particles. Okay, so let's set up the general problem more precisely. We'll use eta to denote the number of particles, and these particles are at positions R1 to R eta. And each position is going to be represented using log n bits of precision. And each particle will also have a charge or mass associated with it. So then the problem is to compute the total potential energy V, which is the sum over all pairwise interactions. So here kappa is the kernel function, which encodes the interaction between two particles based on their positions. And we're going to want to do this computation on a quantum computer. So why do we want to do that? Well, this kind of problem is pretty general. It appears in many different areas of physics. But the setting that's likely going to be most interesting for quantum computers will be quantum chemistry, or more generally, quantum many-body physics. So we're going to work in first quantization of real space. And here, eta will be the number of electrons, and n will be the number of grid points. So we often think of n as being much, much larger than eta. And in this setting, the potential we're going to be interested in is the Coulomb potential, or electrostatic potential, for which the kernel function is given by the inverse distance between two electrons. So the potential energy V has this form up to a constant. Okay, so now more explicitly, what do we mean by computing V on a quantum computer? Well, since we're in first quantization, the state of the electrons will be this anti-symmetrized superposition over their positions like R1 to R eta. And basically, we want to implement a unitary which, given any set of positions and an ancilla register initialized to 0, computes V, or at least some approximation of V, into the ancilla register. And note that even though our state will be the superposition, it suffices to have this unitary act correctly on any computational basis state, because then obviously it'll act correctly on any superposition. So from now on, let's just consider a single set of positions, R1 to R eta. In other words, we can essentially think of this problem classically. Okay. So what's the motivation for all this? Well, like I said, direct computation of the Coulomb potential energy has order eta squared cost, since we need to consider all pairs of particles. The fast multipole method reduces this to linear in eta. Well, more precisely, direct computation has eta squared cost up to some logarithmic factors in n, because each electron position is represented using log n bits. And the complexity of FMM will also have some log factors in n, as well as in 1 over epsilon, where epsilon is the target accuracy. So FMM isn't going to compute the potential energy exactly, but it turns out that it can achieve arbitrary accuracy. But for the purpose of this talk, we're really only going to be interested in asymptotics and not care so much about log factors. So for the most part, we'll put tildes over the big O's to indicate that we're hiding log factors in n and epsilon, etc. And then our goal will be to compute V on a quantum computer using order n gate complexity up to log factors instead of eta squared. And the reason we want to compute V in this way is so that we can then apply a Trotter step with the same complexity. So recall that if we can compute V into an ancilla register, then we can apply time evolution under V using phase kickback. Now, more explicitly, our Hamiltonian in this setting is the electronic structure Hamiltonian in real space, So under the Born-Oppenheimer approximation, it has these three terms, the kinetic term T, the external potential energy U, and the Coulomb potential energy V. And implementing time evolution under this Hamiltonian using Trotter or some higher order product formula is bottlenecked by the computation of the Coulomb term V. So specifically, the kinetic operator is diagonalized by the quantum Fourier transform, so the corresponding Trotter step can be implemented in linear time. The external potential U is actually diagonal in the same basis as V, but unlike V, it can usually be computed in linear time. So V is the only part that has quadratic cost, at least naively, and this is what effectively dominates the complexity of first quantized algorithms in previous work. Okay, so this talk will be about how to reduce this quadratic complexity to linear, and the net effect this will achieve is to shave off a factor of basically eta off the total complexity of any quantum simulation algorithm in first quantization that's based on Trotter or that involves implementing V by fast forwarding. So how will we do this? Well, as the title of the talk suggests, our central ingredient will be the fast multipole method, which does have order eta runtime, but we're going to need to come back to what we mean precisely when we say runtime. And we're not actually going to implement all the aspects of fast multipole precisely, but we're going to borrow some of its main ideas. So before I describe the first main idea, let's define some notation. We'll use phi sub j to I to denote the potential at the position of particle I due to its interaction with particle j. So the total potential at particle I is the sum of phi sub j to I over all of the other particles j. And in what follows, we're going to use this phi notation a bit more generally. So in particular, one of the main ideas of FMM is to approximate the potential between groups of particles that are far apart. So let's say we have two regions, A and B, where the distance between A and B is large, at least relative to the distance between particles within each region. And let's consider the problem of computing phi sub B to I, which is the potential at particle I due to all of the particles J and B. We can, of course, do this exactly by summing over the contributions from all the particles J and B. And this is going to have cost proportional to the size of A times the size of B. Or rather, each of these computations has cost proportional to the size of B, and we do this for each of the particles in A. So the total cost is the product of the two sizes. But because A and B are far apart compared to the space between the particles in B, the potential at A due to some particle in B isn't going to depend too much on where precisely that particle is within B. So as far as A is concerned, things wouldn't look too different if we just took all the particles in B and put them at the center of B. In other words, let's compute the total charge of the particles in B and put that at the center. Similarly, again, since A is far away from B, the potential at B doesn't, the potential due to B doesn't vary too much within A. So we'll compute the potential at the center of A due to the total charge Q sub B of B, and then at the center of B. And then for each particle I in A, we approximate phi sub B to I by just taking it to be the potential that's at the center of A. So what do these approximations save us? Well, the first step, where we sum over all the charges in B, has cost proportional to the size of B. The second step is just a few arithmetic operations. And the third step, where we assign phi sub B to A, to each particle in A, is going to have complexity proportional to the size of A. So overall, the complexity is size of A plus size of B. So we've essentially gone from multiplicative in A and B to linear. And the next question is, well, what's the error in this approximation? So what we're doing here, oh yeah.
Yeah, I I must be missing something here. And the improvement is in the order of eta, which is the number of electrons, right? And then for each electron, you discretize it in space. That's great. And you have a capital N. And you were saying you can use log n qubits to represent that big N. That N is very costly, right? Yeah. So each electron, you discretize it, you have N points, space in space, okay? And then you have this eta. So it would be, in general, would be n to the power of eta. So the eta, the number of electrons, is already in the exponent.
Well, but
because if you have three electrons,
you're representing the positions in binary, so you take the log of n to the eta, so you end up with eta log n.
Sure, but you still have log n to the power of eta. So the eta is actually in the exponent.
No. The eta is in the exponent of n, not in log n.
So
you take the log of n to the eta.
Yes.
So the total number of bits in your representation is n log eta.
Thank you.
Right, so how do we attain arbitrary accuracy? So what we've done here is actually essentially the 0th order approximation. And to get better accuracy, instead of considering like the total charge in B, we can keep around higher order multipole moments. And like the total charge is just the monopole. And instead of just setting the potential at each particle in A to be equal to the potential at the center, we can Taylor expand around the center. And it turns out that to get some error epsilon, it suffices to keep order log 1 over epsilon multipoles and order log 1 over epsilon terms in the Taylor expansion. So this ends up getting some additional log 1 over epsilon terms in the total runtime. And I should mention that I took this diagram from a YouTube video of Letzing giving a talk about fast multipole, and it's one of the most popular videos on YouTube about fast multipole, and it's actually how I mainly learned about fast multipole. So if you want to learn more, you should check out that video. So thank you, Letzing. Okay, so the first main component of FMM is to only approximately compute the potential between regions of particles that are far apart, instead of doing like all the pairwise interactions. But how do we systematically define whether two groups of particles are sufficiently far apart in order that we can use this approximation? So another key component of FMM is to divide the space into sort of a hierarchy of boxes. And we'll say we'll use this approximation whenever the distance between two boxes is greater than or equal to the side length of each box. So more specifically, we'll have these different levels of boxes. So at level 0, we just have the full space. We just have one box. At level 1, we divide the full space into 4 boxes, at least in 2D. In 3D, we're going to divide it into 8 boxes, but we'll always draw things in 2D. And then at level 2, we further divide each level 1 box into 4 boxes, and so on until we reach a level that has n boxes, where, remember, n was the number of grid points. So overall, we'll have log n different levels and order n boxes in total across all of the levels. Okay, so now let's look at how the approximation from the previous slide is systematically applied. Well, at levels 0 and 1, there's really nothing interesting to be done, because at level 0, you just have 1 box, and at level 1, you have 4 boxes, but the boxes are all next to each other, so they're too close for us to use this approximation. Now at level 2, let's consider this hatched box, which we'll label A. So notice that A is sufficiently far away from all of these gray boxes as per our definition. So we can use the approximation from the previous slide to compute the potential contribution from each of these gray boxes. And these gray boxes are referred to as the interaction list of A. Okay, so we approximate the contribution to A from everything in the interaction list, but this doesn't take into account the contribution from these white boxes. And we can't use the approximation for these because they're too close. They're direct neighbors of A. So in order to handle this white region, we have to move to the next level, which we get from dividing each box at this level into quarters. So now let's focus on this smaller red box in A, call it A primed. So again, at level 2, we weren't able to take into account any contributions from this highlighted region. So at level 3, we consider all the boxes that are in this region, except for the ones that are directly adjacent to A primed. So the interaction list of A primed consists of these gray boxes, like everything we ignored in level 2, because they were too close at that level, minus the boxes that are still too close at this level, because they're directly adjacent to A primed. And for these boxes that are directly adjacent, we again have to defer to the next level, which has an even finer spacing. And we continue in this way until we reach the very last level, where all we have left to do are the nearest neighbor interactions, and then we just compute those directly. OK, so putting the previous 2 slides together, here's a sketch of the full algorithm, or at least a simplified version of it. So first, for every box B, like across all the levels, we sum the charges in B. This corresponds to the first step in our approximation from previously, where we took all the charges in B and just put them at the center. And then for each box A, we add the contribution to A from each box B in the interaction list of A. So each of these contributions, phi sub B to A, is what we computed in the second step of our approximation procedure. So phi sub A is like the potential in box A due to all the particles in A's interaction list. And then finally, we compute the potential phi sub I at each particle position. So for each particle I, we consider all the boxes A that particle is in. Remember, each particle is in one box at each level. And in step 2, we computed the potential at each of these boxes due to its interaction list. So we add up all these contributions to phi sub I, and this corresponds to the third step in the approximation scheme, where we took the potential at the center and just assigned it to all the particles in that box. So this only leaves out the contribution from the particles that are direct neighbors of A at the level of our grid, because the interaction lists never contain nearest neighbors. So in this last step, we just add in all these remaining contributions. And then once we've computed the potential phi sub I for all of the particles, then we can use these to get the total potential energy V. Oh, yeah.
And in which step are you accounting for, like, within a particular box, the interaction between each particle within that box?
Oh, yeah, so once you get to the last level, which is just the grid, all the particles are at a different grid point because of Pauli exclusion, for instance. So at the grid level, you consider everything that's the nearest neighbor, and then that accounts for all the particles, all the interactions due to other particles, because they'll either be nearest neighbors at the grid level, or at least at the next level down, then they'll be in different boxes.
At that point, you're not lumping anything together.
You're not?
Like lumping any of the particles together.
Right, but then each particle will only have a constant number of nearest neighbors in the grid. So we'll see this when we get into the complexity analysis. So what's the complexity of this algorithm? Well, it's definitely going to depend on how we implement it. Because, for instance, let's look at the first step. Sorry. So in step 1, if we were to actually iterate through all the boxes and compute the total charge of each, then this would already have order n runtime, because there's order n boxes in total. And we don't want this, because n is usually much larger than eta. But because n is much larger than eta, not all of the boxes will actually contain electrons. And we obviously don't want to compute the total charge for any box that doesn't have any electrons in it. So instead of iterating through like this full stack of boxes, we should only consider the ones that are actually non-empty. And there's going to be order eta log n of these, because there's eta electrons, and each electron is in log n boxes. So in the usual implementation of FMM, these non-empty boxes are organized into like a tree-like data structure such that they can be efficiently accessed. And then this first step would have order eta complexity of the log factors rather than order n. Similarly, in the second step, instead of iterating through all the boxes A, we should only look at the non-empty ones. Again, there's order eta log n of these. The interaction list of each box contains a constant number of boxes, so the total complexity for step 2 is also order eta up to log factors. And in step 3, well, for the first part, each electron is in log n boxes because it's in one box at each level, and there's log n levels. And for the second part, each electron has a constant number of nearest neighbors. So the total cost for step 3 for each electron is logarithmic. And then taking over all electrons, we again have linear complexity and eta up to log factors. So the total complexity is linear up to log factors. And again, to get arbitrary accuracy, instead of just doing this sort of 0th order approximation, we use higher order multipole moments and keep around more terms in the Taylor expansion. And this just ends up incurring logarithmic overhead in the inverse error. Okay, so.
Can I ask a question? Does this analysis really depend on the matrix kappa also? Or if you don't know that there are very few electrons, then how do you conclude that there are very few?
Well, it's analyzed in terms of the scaling with the number of electrons. And for kappa, so like in the case of like the Coulomb potential or gravitational potential or whatever, it's the inverse distance in 3 dimensions. So that's computable efficiently.
And there are assumptions on kappa which make that analysis work? Or
well, I guess the assumption on kappa that you have to make is that like its gradient is small, because you're assuming that the potential doesn't vary too much depending on where precisely your electron is. Does that make sense?
Sorry, what was kappa?
Oh, kappa is the kernel function defining the potential.
Square.
So for the Coulomb potential, it's the inverse distance, for instance.
So I actually had the same question, but so you're not relying on the inverse square law having this property where like a sort of even distribution you can consider it just the center of mass? Like this is like a property of inverse square.
No, I think you just need the fact that, like, again, it doesn't vary too much. Like its gradient is small at the center. And you need it to have like a Taylor expansion around the center, but.
It has a singularity on the diagonal, right?
It has a singularity, what?
On the diagonal?
Oh yeah, but at least for our problem where we have electrons, you're not going to have two electrons in the same place. But like beyond electrons, I'm not sure what you would actually do on a quantum computer. Like you can use this to like compute like planetary motion or whatever, but you're never going to want to do that on a quantum computer.
So what's the dependence on the dimension of the points?
On the dimension?
Yeah.
Oh, like whether you're in 3D or 4D.
Yeah.
Or... Great question. I'm not actually sure, but I'm limiting myself to 3D. Yeah, I'd imagine that it's exponential in the dimension because the size of your interaction list is like.
I mean, if your points are lying in some like a d-dimensional space, then it's like a interaction list of the box will also depend on some.
Yeah, that's what I'm saying. It's probably going to be exponential in the dimension.
Yeah.
But again, we're only going to apply this to at most 3 dimensions.
What happens if you have a system so that every box has at least one particle?
Well, then you still have the right scaling in terms of the number of particles.
So are you ruling out like cases where you can have like a very large density of electrons?
No. As long as your grid is fine enough that each electron is at a different position in the grid.
That's right. And but from energy assumptions, you can probably rule out those cases, right?
Sure, sometimes, yeah.
Would this give you some additional?
Possibly, but I'd imagine that like at sort of like interesting moments in the time evolution, you might precisely want to consider like the distributions where you do have a lot of electrons close together. But yeah, one thing we did think about before doing this like adaptive version was sort of imposing like an energy cutoff and then having some like failure condition there. Any other questions before I move on? Yeah.
So while we're asking questions, so is it possible to get a sense for what the like constant factors might be in this compared to the O eta squared case?
Oh yeah, the constant factors are pretty large, but we'll get to that in a bit. Okay, so we've seen classically that we can do FMM in linear time. So you might be wondering, like, well, what's the problem? Can't I just translate this to a quantum circuit that also has linear complexity? And note that what we're ultimately after here is going to be a quantum circuit, but it would suffice to just have a classical circuit for this problem, since we can always convert a classical circuit to a quantum circuit with constant overhead. So more generally, we can ask the question, well, if we have some classical algorithm with some runtime, is there sort of a general recipe for directly translating this to a circuit, classical or quantum, with the same complexity in terms of the number of gates? And this turns out not to be so straightforward. A classical algorithm with a given runtime doesn't automatically imply a circuit with the same complexity in terms of gate count. Yep?
Yeah. Just ask a question. So you mentioned you're looking at multiple electrons, right? And no other particles. But if you want to study molecules, for example, there are nucleus.
Oh, you can
and then the attraction is going to go almost the 1 over r because they can get infinitely close.
Sure, but then
the derivative is large as well.
Sure, but then you might not want to be considering simulating that in real space. You might consider some other kind of discretization.
Yeah, so it's okay to put some positive charge there, right?
It's okay to put some positive charge as long as, again, it fits into your grid. So like the way I wrote this, like I still have the QIs around instead of replacing them with the same charge E. So yeah.
Kind of confuse myself, I guess, upon set up the problem. So what is given? So you're given a wave function and you want to compute the...
You're given the... You want to implement time evolution under the electronic structure Hamiltonian.
Yeah, so you're given a wave function in first quantization.
Yeah. And then you want to compute the potential so that you can fast forward the potential.
Right, but then if that's the setup, then you're not given any points, right?
You're not given what, sorry?
You're not given like n points in the classical simulation in mechanics.
So what you're given...
In the first quantization, the two offers is diagonal.
Right, it's diagonal, so you want to compute. So we go back to the previous slide, is the first slide. Your state is something of, sorry. This is not the right slide. Oh, I see, there's a transition. Oh no, that's right, there we go. So your state is something that looks like this, right?
No, that's why I'm confused, because in the first quantization, my state is like a sign, which is a wave function embedded on the grid.
Yeah.
It's not a position.
Oh, but it's going to be, like on the quantum computer, this is how it would be represented.
I don't think so.
I'm not sure what you mean by your state as a wave function. I mean, the wave function just tells you
You're talking about first quantization, right? So I have
yes.
a grid.
You have a grid.
And I want to evaluate my many-body wave function on the grid points.
This is the wave function of the multiple electron system.
Right, which will be some like superposition of position states, right? Like the wave function just tells you the coefficients of the superposition. Yeah.
Related question. So at every time step, your system will evolve dynamically. So your
Yes.
particles will shuffle around.
Yeah.
You have to redo this grid analysis at every trotter step.
Yes. So you redo the calculation at every trotter step. That's why the computation of the potential determines the complexity of each trotter step. Yeah.
If it's a molecule, you have many more terms, like the nucleus are also vibrating and rotating, right?
Sure.
So the B is, a bit more. And then you have to somehow antisymmetrize just the electrons, not...
Yeah, but that's... So for simplicity, we're not considering molecular simulation, but yeah, this is like other subroutines that would go into the quantum algorithm. Okay, so back to whichever slide I was at. Let's see. Is there a better way to? Oh, okay. Okay, yeah. So, like I said, it's not so straightforward to just take any old classical algorithm and translate that to a quantum circuit that has the same complexity in terms of the number of gates as the runtime of the algorithm. And why is that? Well, one issue is that the runtime of classical algorithms is often analyzed with the assumption that RAM queries take order 1 time. So here what I mean by a RAM query is you have some array, you write down an index or address, and you want to output the element stored at that index of the array. So as a quantum circuit, or just as a reversible circuit, this is what this operation looks like. It's often referred to as QRAM. So in quantum notation, in the first register, we have some address A that's written in binary, and we also have some data registers. So here we have n data registers. And given any state of this form, we want to apply an operation that brings up the 8th data register to the first position. And this is the usual circuit for implementing this, at least for n equals 8. And you can sort of understand the circuit as follows. So the first 4 swaps are controlled on the most significant bit of A, and they basically check whether the index A is in the first half or the second half. And then they bring up the correct half up to the first 4 positions. And then the next 2 swaps are controlled on the second most significant bit, and they check which quarter the index is in. And you continue in this way until the correct data register is brought up to the first position. So the circuit clearly needs to have at least a linear number of gates because it has to at least touch every data register. And I also don't know of a way to implement it using fewer than linear non-Clifford gates. So similarly, on a classical computer, you can say we also need a linear number of gates in order to retrieve from every location in memory. But the circuit depth is logarithmic in the array size. And in practice, like the runtime isn't so much determined by the circuit depth. It's often overshadowed by other factors like clock speed. Now in the quantum circuit, we could also actually parallelize the log depth. But for fault-tolerant algorithms, we usually work in cost models where the number of non-Clifford gates is the relevant complexity measure along with the number of logical qubits. And this is because each T-gate requires like a very large number of physical qubits to implement. And actually like parallelizing this to log depth would require implementing a T-gate on basically every logical qubit on a lot of layers. So until we have so many physical qubits that we can simultaneously apply a T-gate to every logical qubit, depth isn't really the thing to consider. So the upshot of all of this is that this linear complexity of QRAM essentially implies that every RAM lookup that's made by the classical algorithm translates to a linear cost operation in the circuit model instead of being order 1 cost, as is assumed classically. So in particular, in FMM, one uses like a tree data structure to store the electron positions in order to access them efficiently. And the cost of operations on this data structure is analyzed assuming order 1 queries, order 1 RAM queries. So directly translating the classical implementation to a quantum circuit would incur linear overhead, which would ultimately result in quadratic cost, so not any better than just direct computation. So in fact, in this recent paper by Childs et al., they actually do consider using FMM as a subroutine in their quantum chemistry algorithm, but they basically steer clear of this issue altogether by just assuming that QRAM has order 1 complexity on the quantum computer rather than having linear complexity. So as they say, like the cost of their algorithm would be larger by a factor of eta in the standard circuit model. And they leave as an open question whether linear scaling can be achieved without assuming QRAM has order 1 cost. So this is what the rest of this talk will be about. But before I do that, I also want to point out a different, although sort of related issue that arises when generally trying to go from classical algorithms to quantum circuits, or even just classical circuits. And this is the difference in the complexity of conditional operations. So in an algorithm, if we have multiple different computational paths, as in, like, for instance, if we have some if-else type statements, then the algorithm is only going to take one path on any particular input. And we just count the runtime of that single path when analyzing the complexity of the algorithm. In contrast, in a circuit, at least in a naive translation to a circuit, we'd have to lay out all of the gates corresponding to all of the different paths, because the same circuit has to work correctly on all possible inputs. So the complexity of the circuit, as in the number of gates in it, can be parametrically larger than the runtime of the algorithm. Okay, so how do we reconcile all this with the well-known notion that classical algorithms and circuits are equivalent? Well, the point is that they're only polynomially equivalent, where you can have a different polynomial. Whereas here, we really do care about polynomial factors because we're explicitly trying to go from quadratic to linear. So this general equivalence doesn't really help us. Okay, so those are just some reasons why it's not in general straightforward to just take your classical algorithm and implement it as a quantum circuit with the same fine-grained complexity. And indeed, in this particular case of FMM, we just weren't able to directly translate the classical implementation and get a quantum circuit or a classical circuit with linear scaling for the gates count. So how are we to implement things? Well, first, let's just set up our registers for storing information. So for each of our eta electrons, we're going to introduce log n ancilla registers, essentially one register for each box that it's in. Remember, each electron is in one box in each level of our hierarchy of boxes. So schematically, this is what this looks like. So remember, our state is some superposition of states of this form, which encode all the electron positions. So to each electron position, we attach log n different ancilla registers. So here, for instance, A1 to A log n denotes the log n different boxes that R1 is in. And we're going to use these ancilla registers to store information that will compute about these boxes over the course of FMM, such as the total charge, the potential contributions, and any intermediate computations. And each of these registers will consist of logarithmic number of qubits. So overall, we'll have order eta space complexity up to log factors. And also notice that some boxes may appear in this encoding multiple times because multiple electrons can appear in the same box. So each of the electrons that are in the same box will have a register storing the information about that box. For instance, if we have an electron here, it also will be in these boxes at the lower levels. And if we have another electron here, it'll be in a different box, one level down, but then it'll be in the same box at the remaining levels. So in this sense, we might be encoding information somewhat redundantly, but this really can't be avoided because our circuit has to work correctly on any input, and you can't imagine distributions where all the electrons are in different boxes at all the interesting levels. But one issue, and we'll come back to this later, is that if we do have multiple registers for the same box, then we need to make sure that information about that box gets correctly put into every one of those registers. And also observe that it's easy to figure out which box an electron is in. Like, we can think of the lower levels of boxes as a coarse graining of our grid. So we can just truncate the binary representation of the electron position as we go down the levels. Okay, so this is how we'll set up our registers. And like I said, it's pretty much the only thing we can do. We can only have extra registers for each electron. In particular, we can't directly store all of the boxes because we don't want to have order and space complexity. So that's how we'll store information. But now what do we do? How do we actually compute the information that has to go into each of these box registers? as prescribed by FMM. So let's just focus on step 2 of FMM because it's really going to be the trickiest step to implement. So in this step, remember, we want to compute the contribution to the potential at a box A from all of the boxes in the interaction list of A, so these boxes here. But keep in mind that we can only access box registers through the electron positions. Like, we can't directly look up a box and see what electrons are in it, for instance. So the picture you should have in mind isn't so much that we have this like full grid of boxes, but rather we only have registers corresponding to these boxes that actually contain electrons. And moreover, these registers are sort of attached to the electron position registers. So in this sense, we can only access the information about a particular box through the electron position it's attached to. So then, like, how do we even iterate through the interaction list of A? We know what the boxes in this list are, but for any given box, like, how does the circuit know which register to look at? If you gave me a particular box, we can't even immediately tell where the corresponding register is or if it's there at all without iterating through all of these registers. So a naive approach would be to iterate for one electron, look at all of the other electrons, check if the box containing that electron is in the interaction list, and if so, compute the potential contribution. But this would involve, for each electron, iterating through all the other electrons. So this would lead to quadratic complexity. In other words, not any better than the brute force approach. Okay, so what do we do? As a warm-up, let's consider a simpler problem where we're just in one dimension and the interaction list is just nearest neighbors. And let's suppose that we have electrons that are in these positions. So these electrons sort of turn out to be in these boxes, but I've drawn these boxes in a light color to remind us that we can't access the boxes directly. We can't just look up which electrons are in a given box. We can only access the boxes through the electron positions. So the first thing we'll do is to just sort the electrons by position. So now at least we have them in order. And then we're going to go along and look at consecutive pairs of electrons. And if 2 electrons are in adjacent boxes, we'll compute the potential contribution from the left box to the right box and store that information at the electron that's to the right. So we check this first pair of electrons. We can see that they're in the same box. They're not in nearest neighbor boxes, so we don't do anything. This next pair of electrons are in nearest neighboring boxes, so we compute the potential contribution phi sub B1 to B2, and then store it in the first electron of B2. For the next pair, they're in the same box, not in neighboring boxes, so we don't do anything. And similarly for the next 2 pairs. And then this pair, well, they are in different boxes, but they're not in adjacent boxes, so we also don't do anything.
That's a question.
Yeah.
So, what does the sorting circuit? So
the sorting allows you to go along the electrons and check them pairwise in this way.
What does the circuit look like?
Oh, sorry, what does the circuit look like? You can just use any sorting network, and it has complexity like eta log eta.
Classical. And then turn that into coherent.
Yeah, you can do sorting networks as a quantum circuit. Okay, and then for this pair of electrons, they are in neighboring boxes, B4 and B5, so you compute the potential contribution from B4 to B5 and store it in the first electron in B5. And similarly, these next pairs of electrons are in the same box, so you don't do anything.
What do you mean if they are in the same box, you don't do anything? So you still have 2 electrons there, they interact.
Yeah, but like your operation of computing the potential contribution is controlled on whether the electrons are in nearest neighboring boxes.
Yeah, but if they are in the same box,
then you don't do anything.
They do contribute to the interaction.
But then at the next level.
At this level.
At the next level.
Yeah, so we're only working on one level and seeing how we compute the potential contribution from the interaction list. Okay, so what we have right now is that we have the correct potential contributions, but only at the first electron in each box. Whereas every electron in B2, for instance, has a register corresponding to B2, and that register needs to store the information about B2. So in the third step, we simply go along and copy within each box. So these two electrons are in the same box, so we do the copy operation. This doesn't actually have any effect because we didn't compute anything in B1. These electrons aren't in the same box, so it doesn't trigger the copying. And these electrons are in the same box, so we copy, and then we copy again in this box. So now this box, every box register storing B2 attached to these electrons does have the correct potential information. And then similarly, we do the same thing. So at the end of this procedure, the effect is that all the boxes, including those that are stored redundantly, as in they're stored in multiple electron registers, because multiple electrons appear in that box, have the correct potential contribution from the left neighboring box. And to get the contribution from the right neighboring box, we essentially do the same thing, but we go in the other direction. And you can easily check that each of these steps has linear complexity up to log factors. So this whole procedure has linear complexity, which is good. So this is ideal 1. But that's only the warm-up for this sort of fake problem. Whereas our real problem is in 3 dimensions, and the interaction list isn't nearest neighbors, it's this thing, or whatever its extension is in 3D. So what do? Well, the second idea is to reduce this problem, the real problem, to multiple versions of this one-dimensional nearest neighbor problem that we solved on the previous slide. And how do we do this? We'll do this by sorting in different directions. So what do I mean? Well, let's say we have this hatched box, and we want to get its contribution from this pink box in its interaction list. Then we're going to sort sort of along this direction, and then take the boxes in that direction to be our 1D nearest neighbor problem. And so one way we can understand sorting in this direction is, well, it's easy to sort like left to right, up to down, because you just sort by y coordinate first, and then you sort by x coordinate. So you can apply a linear transformation to all of your electron positions, which essentially has the effect of rotating your grid, and then you sort left to right, up to down, and this is equivalent to sorting like this. Okay, so you can ask, how many sorts do we have to do? Well, naively, we sort for every box in the interaction list. There's 189 of these in 3 dimensions. A simple optimization is to notice that when you sort along this direction, you can get both this box as well as that box. Like these just correspond to the left and right nearest neighbors in our 1D picture. You can't pair up all the boxes, so this reduces the number of sorts to 140 instead of like half of 189. And I'm almost done, so I'll take questions at the end. And just to compare to the classical implementation of FMM, so although this is a rather large constant, I did want to point out that this large constant factor isn't really unique to our quantum or reversible circuit way of implementing FMM, because it essentially appears in the classical implementation as well. So classically, for a typical distribution, you might imagine we roughly have to look at all of the 189 boxes in the interaction list for each box, and for that we do some data lookup to retrieve the data for that box, and then we compute the potential inner contribution. On the other hand, in our circuit implementation, what we're basically doing is, for each electron, we're computing the potential contribution, so very similar to the classical case, plus we're doing, at most, 189 sorts and copy steps. But anyway, the point here is that we're not multiplying the classical implementation by 189. It's more like we're multiplying it by 3 or some small constant. Okay, so I'll wrap up before I get cut off. So basically, using some of the main ideas of FMM, we constructed a circuit for computing the total potential energy using order eta gates up to log factors, improving over the order eta squared cost of direct computation. And this is actually a classical reversible circuit, like all the gates are classical, But we can, of course, realize the gates as quantum gates, so that we can then use it as a subroutine in a larger quantum algorithm. In particular, this allows us to implement each Trotter step with in a first quantized simulation algorithm with linear constant eta rather than quadratic. And from previous work, the total number of Trotter steps you need is this to do Hamiltonian simulation for a time t with error epsilon. So multiplying the two together, we arrive at this total gate complexity. And now we can compare this to the best existing algorithms. So these two first quantized Trotter grid algorithms, the listed complexities result from computing V directly, leading to a quadratic cost for the Trotter steps. So by replacing that with FMM, we essentially shave off a factor of eta. So comparing this to all the other algorithms, we see that our total gate complexity has the best scaling whenever n is less than order eta to the 7, which is usually going to be the case because like if eta is 1,000, then n would be 10 to the 21, which is huge. And finally, as a sort of general remark, we saw that if we're given a classical algorithm with some runtime, it doesn't immediately translate into a circuit with the same complexity in terms of number of gates. So an open question is whether there is, in fact, still always such a circuit. So in the FMM case, our circuit implementation really seems to be like custom tailored to the specific structure of FMM, and it doesn't immediately suggest like a general strategy. So there's really two questions. First, like, is there some general recipe for translating an algorithm into a circuit that somehow preserves the fine-grained complexity? And if there is no general translation, could it still be the case that for any classical algorithm, or at least any efficient algorithm, there's still some clever sort of bespoke way to write down a circuit by exploiting the structure of that particular algorithm, like we saw in FMM? Okay, so with that, thank you for listening, and I'll take any further questions.